This is a cookie, and even if you listen to this and don't see it, you know exactly what it looks like. It's round, it's crispy, and it features delicious-looking chocolate chips. But let's imagine for a split second that I have a means to drastically improve this cookie by replacing the sugar inside with my newly invented sugarium, a substance that has the same sweetening power as sugar, but cuts calories in half and brings a good bunch of vitamins for each bite of that delicious cookie. If you were a cookie manufacturer, would you believe me on the spec sheets and buy it blindly? Well, I doubt it, right? No, you'd probably expect me to put it in a cookie so that you can taste it, and then you'd also want me to put that cookie next to a regular cookie and to blind taste it. Then also give it to a panel so that they can provide you feedback on the cookie's taste, shape, or even smell. And you'd like to check if it changes your cookie production process and if it alters or expands the cookie's shelf life, and if you can source sugarium from only me, or if you have purchasing power because someone else may produce it as well, and so on and so on. Is this fair to me? Come on, I'm a chemist and I just invented sugarium, an absolutely superior molecule. Why do I have to go through all of this? Well,
Watch, learn, and don't eat my cookie.
Because when you want to replace an incumbent that's universally accepted on the market, you have to show, not to tell, that you're better. And you need to demonstrate your pitch in real life. Fair or not, it's a process. Either you're ready for it or everyone will keep eating sugar. Now, I don't know if sugarium exists or will ever be invented, but what I know is that there is a direct equivalent to that metaphor in water tech with membrane materials. Indeed, through the years running this podcast, I've been lucky to encounter many great step changes to membrane technologies, but they all have that one thing in common, whether they like it or not. They had to go through the sugarium steps. Namely, some brilliant chemist or inventor would come up with a new membrane material, like for instance these ceramic elements I got from Sembrane, and would hope for it to get adopted by membrane manufacturers, only to realize that nobody's gonna take a membrane material or element at face value. You'll have to build a module at least, and most probably a full membrane system, then get it tested in pilots, then in full scales and in the real world, for everyone to accept that, indeed, your new material or element is valuable. So, even if what you want to do is market or even license a material formula or an element's design, you will have to go up the value chain, at least temporarily, and produce up to the final skid, or at least commercial-scale modules to be taken seriously. And you may have to do that at scale and for a while, because it's one thing to get adopted somewhere, it's something else to become so much of the new standard that your technology gets a sizable share of the market and is past the tipping point so that you can double down on what you wanted to do all along, which is to produce sugarium and not fully packaged cookies. This was true when John Cadott founded FilmTech in 1977 as a spin-out of the North Star Research Institute in Minnesota and produced the first spiral-wound polyamide reverse osmosis membranes that would become the standard in the early 90s. This is still true today when a membrane, a Zwitterco, an Ala Membranes, a Swirltex, or an Active Membranes need to produce at least commercial modules, if not simply turnkey solutions, to get their material science proven in the real world. This in itself is a major barrier to entry, but also a massive moat once you've entered. As for a FilmTech that got acquired by Dow in 1985 for $225 million once adjusted for inflation, you have several examples of companies like LeakTech, to name one, that are down 98% from their IPO valuation on the back of years struggling to get their silicon carbide material accepted in nanofiltration and reverse osmosis territories. I've said it before, but this is a major reason why membranes, their materials and elements, are the water tech that behaves the most like actual tech. High barrier to entry, tremendous capex needs, but also the greatest potential for scale once adopted. Now, all of that is nice, but it's theory, right? And you know the saying, show, don't tell, so let me show you this empty warehouse. This large, open, and as I said, empty space is actually in Knoxville, Tennessee. And from the day I recorded this on, it's also officially the place where Aqua Membranes expects to produce and scale its membrane spacer business. All that space just for spacers? Well, not really, because like I said, Aqua Membranes, at least for now, can't just market its sugarium. It needs to produce cookies, and they will. How Why? What's the plan? How will it roll out? Let's find out.
The business model that we're focused on in large part is about demonstrating to the sort of the marketplace the value that could be delivered with the elements. Shipping printed leaves requires that somebody wants to buy printed leaves to use in their elements, which is something that we're interested in, but we're still kind of earlier than that, where we're really trying to get the product in the field to get success stories, kind of showing that you can reduce pressure drops, that you can reduce energy consumption, run longer periods of time, to create kind of a market demand to start pulling through the, hey, I'd love to have printed leaves.
Our experience in coming both, especially in CJ's knowledge, but also my own, is that it would be difficult for a Toray or an LG Chem, soon to be Nano H2O, or an Ito Denko to really fully adopt our technology unless it was really de-risked. So the best way to de-risk it is for us to prove it ourselves. So how do we prove it ourselves? Well, we make the modules and we sell to Coca-Cola, we sell to Micron, we sell to mining companies, we sell to Osmoflow. And once we get to that tipping point of there's 5,000, there's 10,000, there's 20,000 aqua membrane elements operating in the field, then one of the majors potentially comes and says, okay, now clearly it is becoming the standard. It is de-risked enough for us. It's also a reason for this building because they manufacture in such volume. I mean, 10x the volume that we have here. They're going to want to see yield, productivity over months and potentially years, not weeks. So the idea of licensing has always been an attractive one. You can make money a lot faster as a startup and responsible for my investors' return. But really, if you want to have licensing on good terms, you really have to be leading it first. And so we also have the opportunity then in a couple segments, we're already starting with this, we bring the customer to one of our potential licensees. Like we said, all right, this customer isn't a fit for us, but they really want the product. Are you interested in making it for them under these licensing conditions, which are much more attractive to us, obviously? When we bring the opportunity, the technology, and the customer, it's a much better negotiation for us. And I think, long-term, it's going to be both. We're going to sell to strategic customers directly, but then we'll also licensing both for markets and geographies that we think might be interesting, and we'll see how far this thing can go.
You started that journey 15 years ago in your garage.
Yes, I did. The concept had been developed. I left my prior employer because they weren't interested in the technology, quite frankly. I took it. I was working out of my house to begin with. I built the first rolling table in my garage, in my house, 2-car garage. And then we leased some space in town and we began developing the technology. And we started with small elements because it was easy to build those things to begin with. But now it's grown into full-scale, commercial scale, 80 by 40 elements. Being a long road, we went from my garage, and then we went to a leased facility, and then we went to a bioscience center, which is an incubator, and then finally into the facility. Got a technology developed and proven, and now here in Knoxville, 200,000 square feet of space to really build this thing out and meet the demand that we know is coming. The technology is very disruptive. We're convinced of that. It's been proven by others. We're excited to be here in Knoxville to get this thing really moving.
On behalf of Governor Lee, I want to say thank you to the company for choosing Tennessee, for adding 95 new jobs and investing $6.5 million into our community. So thank you very much.
Is the 6.5 already spent and the 95 jobs created, or is it like a plan over time?
The 6.5 is already spent. The production equipment is already in the building. So that includes printers, winding, finishing, testing, storage racks, etc. That investment's done. We're at the back end of our B series now. We're almost closed. There's a little bit more room. Anybody wants in at the end. But yeah, we plan to close down the B series by the end of the year and then use that funds to grow and fill the building. This building has capacity for up to 25,000 elements with the equipment we have. And once we get that sold out, then it's very modular. We took about a quarter of the manufacturing space in this building, so we can expand many times. 95 employees will grow into as we add shifts. So we'll do one shift through probably Q1, Q2 we'll add another shift, hopefully Q3, Q4, the third shift will come on, and then we'll get up over that 95 number.
When did you decide you needed to build a big factory, and how did you land in Knoxville?
In Albuquerque, we were developing the technology, and we were building enough elements to work with companies like Micron Technology and Coca-Cola and Osmoflow in Australia. Technology clearly was demonstrated. Everything I thought it might be 15 years ago, it has turned into and more. As people, the big companies like Micron and Coca-Cola and others see how effective it really is, how disruptive it really is, they're beginning to ask for more. We can't do it in Albuquerque. It's just not nearly big enough. So we went out looking for a large facility. We evaluated 20 different locations in the United States and in Mexico. and landed in Knoxville. For the business-friendly environment, as evidenced by all the people here in community, in city, and county, we want to thank everybody for that activity. That's business-friendly environment here in Knoxville. We've got a good educational system, good resource base. Knoxville is where we landed after evaluating 20 different locations, including Mexico. This is where we're at. This is where we're going to grow. We've got a nice new facility here to really get it in production.
So you keep one leg in Albuquerque, one leg in Knoxville.
Yeah, the Albuquerque facility will continue to be an R&D and development center. We actually bought all the manufacturing equipment we have here first in Albuquerque. The semi-automated winders, the printers, they're all the same. That'll actually reduce our time to get this plant up to capacity and yield because we're using the same equipment. New people, but same equipment. And then it also gives us the benefit if we ever have yield or quality issues here, we can go back to Albuquerque, replicate, do some testing without interrupting production. Then the other big element of Albuquerque will be what we call our co-creation process. So this is the idea of taking new membrane, new patterns, new applications, maybe even not in water, maybe in a gas separation. Somebody wants a flow channel produced and printed, and that allows Albuquerque to focus on that and kind of unique different printings and small runs. And this is high volume manufacturing.
Now, when you deploy a new membrane technology and want to try it out, you probably will want to take some samples and get them tested, right? Well, if that's the case, you'll want to hear from today's sponsor, Simple Lab. Indeed, testing water and everything around it should be simple. With Simple Lab, you choose what to test, from drinking water and wastewater to soil, air, food, and surfaces, and they handle the rest. Kits arrive at your door with free round-trip shipping, samples go to certified labs, and results come back fast, concise, and actionable. Trusted by leading brands and growing teams, Simple Lab offers hundreds of ways to better understand your environment. Get started today at gosimplelab.com. It's the first link in the description. Thanks, Simple Lab, for supporting my work. And before hearing more from Craig and Rodney, let's go on a factory tour with CJ.
I feel like we should have a bell or something too with these 10-minute windows at each of the unit ops. Let's go ahead and start out with leaf prep. So the very high level, the process of making the elements starts with the flat sheet membrane, which we'll see at the printing stage. The clean side is handled by these two machines, and we'll go down to this one just because it's got some material set up with it. This is the material that conveys the purified water through. The holes in a reverse osmosis membrane are very, very small. They're about 6 angstroms, so the size of 2-3 atoms side by side. So it takes a fair amount of pressure to push the water through. So this pretty tight material is what's used to keep that channel open so that the water can flow through to the center tube without being crushed. Overlooked material, but pretty important in the longevity. Any issues with kind of the consistency of this can be places where the membrane can start to deform, eventually break or crack, leading to salt loss and shortened lives. This sets the overall design of the element as well. We're basically taking a long piece of material and then a number of ones that get welded onto it to add other ones. So this machine will get the right dimension, cut it, and then sonically weld one material to the next material to the next material. And that becomes kind of the skeleton of the element. We'll end up taking the printed membrane leaves, interleafing it, and then it all comes together at the rolling table where we do the assembly of the actual element. As you can see, this is printing. This type of printing would be most commonly used for making like billboards. So you take a piece of paper through here, print it wide, print it long, glue it up to a billboard. So what we've done is modified it a few things. The first is to be able to print on top of itself more times to build up height, to build up texture. We've also needed to work a lot on the actual resin that's being applied. Normally it's meant to print on a membrane, not necessarily build up. So there's changes both for getting good adhesion to that RO membrane and to be able to build with kind of minimal spread. That purple light that you see is actually an ultraviolet light that cures the chemistry. It's actually pretty similar to the material that would be used in like a dental filling. It's a polyacrylate with an initiator in there so that when light hits it, it goes from liquid to solid almost instantly. The pattern itself that's being applied is actually our second generation print pattern. We started with something that was much more similar to what's commonly used in the industry, the kind of crossing points of that mesh netting. As we started to do more work on the way that fluids flow through it, we realized that we could make it more efficient by starting to offset the print locations. The kind of spiral design you see is actually based on a Fibonacci spiral, which was an easy way for us to be able to make sure that there weren't straight line gaps where the fluid could flow without hitting features. A couple other things to note, that blue section through there, when the membrane is kind of processed, the next step actually right behind us here involves folding that over. That thin reverse osmosis membrane is just a few hundred nanometers thick. So we realized we could also just modify the print. So we changed the print pattern to put that blue stripe on there to deaden the area where that fold happens to protect it that way. It's better adhesion, it's less material, and it saves us a process step. The line pattern on the inlet and the outlet serves a couple of purposes. During the rolling step, that's important to be able to make sure the glue penetrates well. It helps distribute the force through the rolling process. And later on in the manufacturing process, there's actually a cutting machine that cuts the edge off, and that makes sure we have a good inlet and exit from the element, that there's a nice uniform channel for the flow to enter the element and leave the element. The membrane is taken up on that roll, but to make it into elements, we need to break it into individual leaves. So that's what's happening in this step. We'd have a roll of membrane. We actually print about a meter of membrane, and then we have a gap region and then another printed region. The reason is because once we print it and fold it, the print pattern that we print on the one side matches up with the membrane on the other side to create that channel. So in the folded state, you can kind of imagine what that channel is, and the water would need to be kind of serpentining around those posts that we print.
Is this going to be more automated at some point?
Eventually, these become like a single machine with light curtains around it, where it's raw materials in, elements spitting out the back.
Yeah.
And it's just a series of automating the points that are taking the most amount of labor, become more efficient at that overall process. This is really the last piece of what we'll be seeing in this portion of the facility, and this is the rolling process. This is where all the different pieces that we've seen so far kind of come together. You can see the robot arm is what it's actually doing is applying a bead of glue around the perimeter of that, and that seals one of the membranes through the permeate carrier to the next membrane. It's kind of sealing almost an envelope where the only open side connects to the center tube. The center tube has a bunch of holes drilled into it so that the water can make it through the membrane, through the permeate carrier, through the center tube, and then it's isolated from the feed. So that bead of glue is pretty important in that it separates the feed high pressure from the clean water. If there was any gaps in there, the feed would just go sideways through the edge, and you would lose that separation of the salt water and the purified water. By automating the glue line, we're actually able to get more active area into each element. So the next step after this is rolled would be cutting the edges off. That needs to be very precise because we've got 29 of these glue lines, and if one of them is off, you could get to a situation where you cut on the wrong side of it and you end up having a defect area. So by automating this, we can be very precise with the location of those, make the glue line smaller, which opens up more of that internal area. So going from the hand-rolled process to this automated, we gained about 10% active area. Once it's cured, it keeps spinning to make sure that there's no sagging. It takes about 6 hours or so for the glue to go from the liquid state to a solid state. And if it wasn't spinning, there's ability for it to flow and end up kind of oblong, and it needs to be cylindrical to fit inside the pressure vessels. This is kind of the initial. Then at the trimming station, there's a saw that cuts right through that glue line, and it's easy to tell because that's where we've got the denser edge pattern, which squares off one end. We square off the other end, then fiberglass is applied around it to kind of further contain the pressure. And then at that point, it's ready for testing. And so as you're seeing them rolling up, we've got kind of the final process. You've got the 29 leaves, they've all had the glue applied, and then it's rolled up into the final diameter. The next step that we'll begin to see is putting tape on to hold that shape. So as it comes together, there'll be a person who applies the roll of tape, starts working back and forth, and they'll be checking to make sure the OD, the outer diameter of the element, is right on. The tolerance needs to be pretty precise. A millimeter too long, you won't be able to get the elements into a vessel. The diameter gets too big, it won't fit into it. If it's too narrow, you need to build up too much fiberglass and you lose active area. So there's a lot of work kind of focused on making sure all the pieces have the right tolerance to be able to stack up into the final product dimensions. So here they're checking the diameter with some pie tape. We're just about done with the rolling step. This is where we're doing the trimming. And it's actually a good place too to be able to see the holes in the center tube. If you get closer to it, that's where the purified water would be finally collected before it ends up exiting. But that element that we saw with the tape, but the unfinished edges, that would be loaded into here. Blades come through, do both cuts. Pretty quick process, pretty straightforward. There's some quality control things that we can do ahead of time. It's pretty common in the industry to do what's known as like a vacuum decay test. So even without putting any water in it, we can pull a vacuum on the center tube and look at the way air comes through. If too much air comes through, we can be assured that, hey, there's some defect in there that we can fix before it goes through further processing. This is where we're applying the fiberglass on the outer shell. The strands of the fiber actually come through the backside. The two components of the epoxy gets mixed right upstream and then it's applied through. You're trying to get that right blend of fiber and the epoxy, sort of the glass phase. So this allows us to automate a lot of that process. And then after that, they again do some curing, this time for the fiberglass. This is also kind of gives it the final finish. And then the last step is some performance testing. So this is pretty similar to the type of system that these would eventually be used in, but it's modified a bit because the typical systems, it's you load it in and then you let it run for 5-6 years before you take anything out. We're consistently, putting things in, running them for 15-20 minutes, taking them out, boxing them. So it's meant for a little bit more high throughput. The membrane elements would actually get loaded into these steel vessels. And so we've got feed solution coming through the backside. Permeate ends up getting collected in some of these lines so we can take samples. It's pretty easy to measure conductivity as a way of knowing how much salt is in there. So we have tanks with, a set amount of salt and we can measure the rejection. We do constant pressure so we know if they're producing the amount of water that they need to. So it's a quick way of being able to measure the performance doing what they'll be doing in the final state. After the testing, goes through preservation, packaging, palletization, and then it's off to customers. What we should really do is get some kind of a rollerblade track through here.
Or go-karts.
That would be fun, yeah. We were joking about it, like a pickleball court or something too.
I noticed on the walls of the building simple flyers saying that you have simple company goals and very clear and articulated company goals. One of them, if I recall right, is 3 proof of concept key customers. Wouldn't you have those already?
We do. Our vision, we have lots of customers, big marquee customers like Micron and Coca-Cola, but really our goal there is to become the preferred supplier, not an approved supplier, but the preferred supplier. So that every time one of those customers says, hey, we need replacement membrane elements, they first look at Aqua Membranes and evaluate us against the values we can produce, the cost savings we can bring. So that's really our goal over the next maybe 12 months, is to get at least 3 of those really big corporate multinational companies that we become their preferred product, not just an approved product.
You didn't name Osmoflow. Still, whenever the topics of your Series B or of your plant opening comes up, usually the first comment you read on LinkedIn in Global Water Intelligence is, if you do it with Osmoflow the way it is starting, you made it. I take a shortcut.
Yeah, Osmoflow is our largest customer. They're buying in bulk. They're our first distributor. All of our other customers are direct end users, but Osmoflow by far and away is our largest kind of partner distributor. They have exclusive distribution rights in Australia and New Zealand, and they're killing it. They've put more installations in Australia than anywhere outside the US. So we love our partnership with Osmoflow. We also love their pushing us. So they often bring us new designs or new ideas of, hey, can your technology solve this problem? Yeah, but that's something in the future for us to do. But yeah, they're definitely pushing us. Love the partnership with Osmoflow.
I got it right. You can 9x your production out of that place. You have the space to do 9 times the module you already have.
Right. And we have new technologies that are coming, we're working on, that'll make this go a lot faster and cheaper, lower cost, let me put it that way. So it'll help our return on investment, our cost of goods and that kind of thing.
I heard of a potentially new generation of printing. Is that on or off record?
We'll call it new. We won't use the name of it yet, but yeah, there's a new printing technology coming that will allow us faster print speeds, more chemical tolerance, temperature tolerance of the product, and lower our cost. So we'd expect to probably launch that 2027. 2026 will be evaluating, proving that at volume. But yeah, there'll be another innovation on top of printed spacers 2.0 or whatever we're going to call it.
So that means the process in these cases would be Albuquerque tests it out. When it's then mature enough, it moves to Knoxville. And when you can prove the concept sufficiently in Knoxville, the full market can get
Correct. And we're actually a little further. We've already been doing it in Albuquerque for about a year.
I see.
We'll start doing it here in March. So by hopefully September, October of 2026, it'll actually be commercial from the standpoint of we'll offer it. Then it really gets interesting back to the licensing discussion, because it does also make the technology much more attractive on the licensing market.
Today is the opening of Knoxville. Did you make it, or is it just a step in the journey?
Oh no, just a step. Oh, this is a beginning step. No. We got big dreams and big aspirations. I want to fill this building and then fill another one. This is by no means making it.
Well, of course, I've never started something like this and seen it grow this big. New technology disruptions, the idea was great. I have to admit, it just grows and it just gets bigger and bigger. And finally, at some point, you just have to really bite the bullet, get some investors involved in helping us grow this thing and grow. But we know the volume, we know the market size is huge. For our company size, it's unlimited, essentially. We're excited to be able to produce these things and get them out there in the field and meet the demand that we know is coming.
You mentioned that your Series B is almost close, but has still a little bit of wiggle space. What type of investor are you looking for?
A good partner. We love investors that can bring more than money. There's plenty of people out there that can bring money, so we're looking for connections, or really ideally, a corporate strategic investor that could be a customer as well as an investor. Lots of corporations out there have big CVC arms.
Isn't it dangerous at your stage to have a strategic investor?
No, it's actually better to have more because we already have a couple.
Okay,
and so
I
our
see.
strategy isn't 1 or 2, but 6 or 8. Because if you have 6 or 8 around the table, then you already have a good mass that would look at seriously an acquisition when that time comes. And you wouldn't have 1 or 2 that everybody thinks, oh, it's an inside job. So we already have Karita, Osmoflow, Pentair in the cap table, and looking to add another 3 or 4.
Water entrepreneurship is not an easy journey. It's a lot of bumps. Yeah, it's a bumpy ride, let's say.
It is, yes.
If you had to look back to the Rodney 15 years ago, what would you tell him?
Of course, you make a lot of mistakes along the way. I wish I had the mental acuity or whatever to skip past some of those mistakes along the way and accelerate this faster. But it's been a good learning experience along the way. We've got a lot of good people involved along the way. It's getting there. So what I say to myself, I don't know that I'd change the way I did it. I basically did it with family money and local angels and kind of grew it incrementally to get the value up before we started taking on venture capital money. Some people got a new technology and they go straight to venture money. I've always wanted to maintain some level of control. To do that, you kind of have to bring it along in baby steps, and then grow it up to something we've got here today.
You're proud of what you have here today?
Oh, absolutely. I'm very proud.
And I believe we would all agree that Rodney has every right to be so. Now, if this kind of growth story is of interest, have a look here to watch my exploration of Membrane's growth journey. Remember that for all your lab testing needs, Simple Lab has you covered. It's the first link in the description, and I'll see you next time.